You ever just look around and wonder what all this stuff is actually made of? I mean, really, deep down. Well, that's exactly what we're going to do. We're going to go on this incredible journey from the biggest things you can imagine to the smallest things possible, trying to find the ultimate building blocks of, well, everything. So you ready? Let's dive in. I mean, just look at this. Our universe is just mind-bogglingly huge. You look out there with a telescope and you see galaxies upon galaxies, right? Each one just packed with billions of stars. It's almost too big to even think about. But here's a crazy thought. What if the biggest secrets aren't out there in the vastness of space, but in the other direction? What if they're hidden in the unbelievably small? And that is the question, isn't it? It's the one that's kept scientists up at night for centuries. If we could just keep zooming in, I mean, way past the everyday stuff, past molecules, past everything, what would we find at the very, very bottom? What's the real, fundamental stuff that makes up the universe? Okay, so to get to the bottom of this, we're going to do something I like to call peeling the cosmic onion. We're just going to peel back the layers of reality one by one. And the first layer? Oh yeah, you'll definitely remember this one from high school chemistry. You know, for the longest time, we thought the atom was the end of the line, the final answer. I mean, the word atom literally means uncuttable. It's that classic picture, right? A little nucleus in the middle with protons and neutrons, and then these electrons just zipping around it. It's a great model. It's simple, it's elegant, and it explains so much about the world we see. But here's where it gets really cool. It's not just some chaotic mess of electrons buzzing around randomly. No. The subatomic world is incredibly orderly. It has rules. Electrons can't just hang out wherever they want. They're locked into these specific energy levels, these shells. Think of it like planets stuck in very, very specific orbits. And the rules for these shells are surprisingly simple, at least at first. The first shell can hold max 2 electrons, the second one holds 8, and so on. Now, this isn't just some random trivia for a test. This predictable, orderly structure is everything. It's what makes a carbon atom different from an oxygen atom. It's literally the foundation for all of chemistry. So, okay, we've got our protons, our neutrons, our electrons. Everything's neat and tidy in its little shells. Seems like we've got a pretty complete picture, right? Case closed. But are they really fundamental? Are they the bottom layer of the onion? Or can we peel it back even further? You know what? Let's peel that next layer. Because that's exactly what physicists did. They started building these massive machines, particle accelerators, and just smashing atoms into each other at incredible speeds. And what they found? Well, things got a lot weirder. It wasn't simple at all. They uncovered this whole new particle zoo of bizarre, exotic stuff. And that's when they had the next giant aha moment. It turns out protons and neutrons, they're not fundamental either. They're not the bottom. Each one is actually a little bundle of 3 even smaller particles called quarks. Yep, we have officially peeled another layer, and we are definitely going deeper down the rabbit hole. But quarks are, well, they're weird. You can't just reach into a proton and pull one out to study it. It's impossible. See, the force that holds them together, the strong force, is just bizarre. It acts like this unbreakable rubber band or a string. The harder you pull, the stronger it gets. And if you pull hard enough, all that energy you put in just snap, creates a brand new pair of quarks out of thin air. The takeaway? You can never, ever find a quark all by itself. So let's step back for a sec. The big picture here is that all the matter you see, everything in the universe, boils down to just 2 basic families of particles. First, you've got the quarks. These guys are the social ones. They clump together to make bigger things, like our protons and neutrons. And then you've got the leptons. This is the other family. They're more like the loners. This group includes our old friend, the electron, and also this super weird, nearly massless particle called the neutrino. Okay, so we have this whole particle zoo, right? Quarks, leptons, it's a mess. What we need is a zookeeper. We need some kind of framework, a set of rules, to make sense of it all. And what scientists came up with? Well, it turned out to be probably the single most successful theory in the entire history of science. And here it is. It's called the Standard Model of Particle Physics. This is it. This is our best understanding of all the fundamental bits of matter and how they interact, how they talk to each other. You can think of it as the universe's rulebook, and it is stunningly successful. It explains pretty much everything. Well, everything except gravity. And yeah, that's a big one. We'll get back to that little problem later. So here are the ingredients in our cosmic recipe book. The Standard Model lays out these 12 fundamental matter particles. They're called fermions, into those two families we talked about. You have 6 flavors of quarks, and you gotta love the names: up, down, charm, strange, top, and bottom. And then you have the 6 leptons, which includes the electron and its 2 heavier, less stable cousins, the muon and the tau, plus their neutrino partners. Okay, so we've got the ingredients, the matter particles. Now for the rules of the game, the forces. And this is a huge idea. Forces aren't just some vague, spooky thing. They're actually carried by other particles, called bosons. It's like the particles are playing catch to interact. So the strong force, which holds quarks together, it's carried by the gluon. Great name, right? It's literally the glue. Electromagnetism is carried by the photon. That's the particle of light. And the weak force, which handles radioactive decay, is carried by these 2 really heavy particles, the W and Z bosons. All right, deep breath. We've gone all the way down to the very heart of matter. Now, let's do the opposite. Let's zoom all the way back out and see how this tiny, weird collection of particles and rules actually built the entire cosmos. Right after the Big Bang, for a tiny fraction of a second, the universe was just this insanely hot, dense soup of free-range quarks, leptons, and photons. They were just zipping around everywhere. But as the universe expanded and started to cool down, the rules of the Standard Model kicked in. The gluons started doing their job, grabbing quarks and gluing them together into the very first protons and neutrons. A few minutes later, those started clumping together into the first atomic nuclei. But it wasn't until about 300,000 years later that things cooled off enough for electrons to finally get captured by those nuclei, forming the very first stable atoms in the universe. Amazing. But here it comes. Here's the biggest, most humbling twist in the entire story. All of this incredible, beautiful Standard Model that we've just figured out, it only explains the stuff we can actually see and touch. And all of that stuff, every star, every planet, you, me, everything, that's only about 5% of the universe. 5%. The vast majority, something like 27%, is this completely mysterious stuff we call dark matter. We know it's there because of its gravity, but we have no idea what it is. So where do we go from here? What's next? Well, physicists are working on some truly wild, mind-bending ideas to explain these mysteries. There's supersymmetry, which says that every particle we know has a heavier, hidden superpartner, and maybe one of those is dark matter. Then there's string theory, which is just beautiful. It says if you could zoom in far enough, you'd see that particles aren't points at all, but tiny vibrating loops of string. And of course, the Holy Grail, the ultimate prize, is a grand unified theory, a theory of everything. A single elegant idea that finally unites all the forces, including gravity, into one beautiful picture. So look how far we've come. We started with galaxies, we zoomed into atoms, and then all the way down to quarks. We peeled back the layers of this cosmic onion. We built this incredible, powerful Standard Model, only to discover that it just describes the tip of the iceberg. Just a tiny slice of what's really out there, which really makes you wonder, doesn't it? Have we finally reached the very bottom of the onion? Or is there another layer, something even more fundamental, just waiting for us to find it?